Hi guys, we are going to jump into some notes today on our next chapter, which is chapter 8 in the book. It's all about energy sources and the environment. So energy sources, we're going to talk about renewable and non-renewable energy sources, and then their effect on the environment. So 8.1 gets into the non-renewable energy sources. We also call them fossil fuels. So take a minute to think about how you use energy every day in your life. We require energy for almost everything that we do in our day-to-day lives. In the US, we rely on energy. This is the breakdown of how we use our energy. So most of the energy use comes from industrial. So this is manufacturing and agriculture uses 31%. 28% comes from transportation, so driving cars, buses, planes. Here we are, residential use, so heating our homes, cooling our homes, electricity for our lights is about 22%, and then 19% of the energy use comes from commercial use. So these are businesses, heating office spaces, cooling office spaces, shops, stores, things like that. All right, so we get that energy mostly from non-renewable sources. So coal, right here, 22%, oil or petroleum, 38%, and natural gas is 25%. So that's what, 25, 20, 40, almost 80 something percent of our energy comes from non-renewable sources like fossil fuels. Nuclear power up here is another non-renewable source, but it's a little different than fossil fuels. We'll talk about that when we get to 8.2. And then these other sources right here, hydroelectric, so water, biomass, geothermal, solar, wind, these are renewable sources of energy. Talk about those later. So most of the energy used in the US comes from burning fossil fuels. And there's a big misconception that fossil fuels come from dinosaurs just because of that word fossil. But it's not the case. Dinosaurs lived about 65 million years ago. Fossil fuels formed hundreds of millions of years ago, 150 to 300 million years ago. So fossil fuels, the coal and the oil and the natural gas that we're burning today is way older, formed way before the dinosaurs even existed. So keep that in mind. Don't fall for that misconception. Okay, they do not come from dinosaurs. So what are they? They're non-renewable. They're carbon-based resources, like I said, formed up to 300 million years ago from remains of dead organisms. So dead plants, dead animals, when they die, they fall to the ground, they decay, they get buried further and further underground over millions of years. It gets pressurized and it forms coal, oil, and natural gas. We're going to watch a video later. All right, so then we extract those fossil fuels from the ground by mining or fracking, and then we burn them for energy. So when we burn a fossil fuel, that's called combustion. Combustion is when you take an organic molecule like coal, oil, natural gas, something that's made of mostly carbon, and then also hydrogen and oxygen. It's called a hydrocarbon. Almost forgot that word for a minute. When you burn something, you add oxygen to it, and all those molecules get rearranged, all those atoms get rearranged to form carbon dioxide, water vapor, and heat. So a combustion reaction is anything that's burned to produce these three products. Okay, and then that has a big effect on the environment, and that's what we'll talk about as we go through the chapter. So what's happening is the chemical potential energy that's stored within the bonds of a hydrocarbon, like coal, gets converted into heat energy, and then also eventually maybe electricity if you're burning it for electricity. And we'll talk about that in a minute when we look at the power plants. All right, so oil, we'll talk about oil first. Oil forms mostly from decomposed marine microorganisms like plankton and algae. So things that live in the ocean. And then over time, once they die and decay and fall to the ground, they're buried under layers of sediment and rock. So this is what I was talking about before with a hydrocarbon. This is an example of a hydrocarbon. So within these bonds right here, see if I can get a marker. Right here, there's chemical potential energy stored in those bonds. And when you burn this, you break those bonds and release that energy. That chemical potential energy gets released, and that energy can be transferred into a different form that we can use for energy. Okay. So here's some examples of microorganisms that might live in the ocean that might eventually form oil. And then also natural gas forms the same way. So this is what the process looks like over time. You have the marine organisms living in the ocean. Eventually, they might get buried under layers of sediment and rock until eventually oil forms. So to access that oil down there, we need to drill for it. So this is called an oil drill or oil rig that will break through those layers of sediment to access oil. Natural gas forms the same way. Since gas has a lighter density, it's a less dense substance than oil, it will float on top of where oil is. So usually oil and natural gas are found together. So this is a map of where the largest oil reserves are in the world. So countries with access, so Canada, Russia, we import oil from some of these countries. So as you can see, US doesn't, we do have access to oil, but we're not one of the largest oil reserves. So we have to depend on other countries for oil. All right, so to find where the oil is, this is gonna sound familiar. Like how do we know where to drill and where there is oil? This is a very expensive process. So if they're gonna drill for oil, they wanna be pretty sure that it's going to be there. So what they do is they use earthquake waves. Remember we talked about how we know the outer core is liquid because S waves can't travel through. And then we also can detect a change in speed of earthquake waves that might indicate that there's a boundary and there's different materials that the waves are trying to get through. So they use the same kind of process to figure out where oil might be, since oil is a liquid. And that's called a seismic survey. Okay, so like I said, drilling is a pretty expensive production. So they have to kind of guess where the oil and gas is going to be and then drill for it. And this gives you an idea of cost. So $10,000 for each meter. So think of like a meter stick. If they drill and no oil is found, it's called a dry hole. So you can look at this website if you want. It's the energy organization from the government that will give you an idea of how many dry holes they actually come across when they drill. It's quite a bit. Okay, so once oil has been extracted from the ground, it has to be sent for processing. And you're going to read about this tomorrow in the book for 8.1. Oil is made up of different types of chemicals, and we can only use certain types for certain things. So it needs to be refined and then transported. So it could be transported by a pipeline. There's one through Alaska. It's called the Alaskan Pipeline, or a massive oil tanker, those giant ships that you might see in the ocean. And then it's refined for different uses. So we use it for transportation. Gasoline in our cars, we use it in a power plant to generate electricity. It's also used to make asphalt or wax. It's used in plastics. I think there's a big picture, of all these different uses for petroleum or oil. So it's not just for oil for our cars. It's used to make plastics, pills, all kinds of things. All right, and then natural gas, I touched on a little bit. It forms the same way that oil forms, and it's usually found, this picture shows you, it's usually found floating above oil. Natural gas is mostly composed of methane gas, but butane and propane could also be found within natural gas. Natural gas is more efficient than coal or oil, which means that it generates, or it contains, remember we talked about how there's chemical potential energy within the bonds of those atoms. So there's more energy per kilogram than coal or oil, which makes it more efficient. It also produces way less pollutants like carbon dioxide. And it's used, a lot of people use natural gas in their homes for their stoves or to heat their homes. It's colorless and odorless. So what they do is they actually add odor to natural gas, just so that if there were a gas leak, you could smell it and know that something was up, because that wouldn't be good if you couldn't smell a gas leak. Okay, and then the process to release natural gas, only natural gas, is called fracking. So what they do, you might have heard of fracking as a controversial issue in the news. There's a lot of people against it because it can be harmful to, if you look at this picture, see there's groundwater sometimes near where natural gas is found. So what they do is they pump in highly pressurized water and sand and other chemicals to break apart rock and release the natural gas. So there's a risk of contaminating the groundwater through this process. So a lot of people don't like fracking to be done near where they live because their groundwater could be at risk. Okay, so we already talked about that. There is risk of pollutants there getting into the water. So then the last fossil fuel is coal. Coal, so we talked about oil and natural gas are formed from marine ocean organisms. Coal forms in more swampier areas. So it's remains of swampy tropical plants and animals that are buried under mud over time with no oxygen. That pressurizes the material and creates peat first, which is kind of like really fertile, dense soil. And then over time, I think there's a picture in the next one. Yep. Over time, that peat becomes even more pressurized till eventually it becomes coal over hundreds of millions of years later. All right. So then once we've extracted those three types of fossil fuels, coal, oil, and natural gas, from the ground, we have to combust. We have to go through combustion, burn it. So this example is a coal-fired power plant, but the same process works for oil and natural gas. So what happens first is that the hydrocarbon, coal, oil, or natural gas, is burned. So that burning process converts the chemical potential energy into thermal energy, heat. That heat is used to boil water, to make steam, and that steam is pressurized and it's sent through these pipes to eventually spin a turbine. So that thermal energy gets converted into mechanical energy with the spinning turbine. That turbine powers a generator, which takes the mechanical energy and converts it into electric energy, electricity. And then the electrical current is transmitted through power lines to your home, businesses, schools. So overall, this process is not very efficient. So out of the 100% of chemical potential energy that was stored within the coal, only 35% of that energy gets converted into electricity. The remaining 65% is lost as heat, as thermal energy to the environment. So not a very efficient process. All right, and then just a quick look at where coal is found in the US. We have a lot of it here in our country. So you can probably notice that where the coal is correlates to where we have mountain ranges. So out here we have the Rocky Mountains. Here's the Appalachian Mountains here. So there's coal reserves usually where we have mountain ranges. So we talked about how burning coal is not very efficient, but we still do it quite a bit because we have it here. It's in our country, so it's safe to ship. You throw it on a truck and move it around. It's cheaper to extract. We have it here in the US. We don't have to import it from another country. So it's cheap. But there are definitely costs of coal, not money costs, but cost to the environment. So it releases a lot of carbon dioxide into the atmosphere, which is leading to overall global warming and climate change. Extracting coal is a very dangerous process for the environment and for the workers, for miners. There's many hazards associated with mining. Okay. So I'm going to leave this math challenge as a question in the Ed Puzzle. See if you can do it. So if it takes, this is a much easier question than it looks like. So if it takes roughly half a kilogram of coal, which is about 1 pound, to produce 1 kilowatt hour of electricity, and the average family uses 11,000 kilowatt hours per year, how many kilograms of coal would this be? So you can pause the video and work this one out on paper and then answer it in the Ed Puzzle. And that's it for 8.1. We're going to talk about this more when I'm back in school next week. And for the rest of class today, you're going to look at an interactive. You're going to burn some of these fossil fuels and see how much energy is generated. Ready? Thank you for listening.